Okay, we can go. So let us now turn to the type of models into the 2D and 3D to two-dimensional, three-dimensional models, which are certainly much more interesting for tackling the real problem that are of interest to engineers. So in this part, I would like to kind of revisit what we are doing in the first lecture, that is the linear and nonlinear elasticity, and basically show you that in 2D and 3D problems, the steps are identical to solving the 1D problem by using the finite element method. The only difference is now in 2D and 3D vision of the world, you kind of realize that there's many more things going on just as opposed to dependence with respect to one coordinate axis that you can conveniently choose to have a one-dimensional model. So the first challenge is really to kind of put the order into what you're observing, and the question notation is certainly not very innocent. I would say that many choices of notation made the books certainly appear much bigger than what they are really. And in particular, classical engineering notation, I remember studying books with the strength of material type of thing that the exam we were taking at Berkeley, a colleague of mine saying I didn't learn anything else but a strength of material because we were preparing something called preliminary exam. We have mathematics and 3 other subjects. And because there's such a, to him, wide variety of different cases, but actually the only case is always there's certain whatever stress components, and you suppress some, you keep some, and so on and so forth. So if you really want to make a point that 1D and 3D have the same physical problem you're studying, it's just different, let's say, vision, better glasses in 3D than in 1D. The role of notation is very important. So I'm using here something called direct to tensorial notation, which splits the problem in 2 steps, which is basically first you take a bold-faced letters that are the same letters as you use in 1D case. The only difference behind this bold-face is hiding many, many different components. So visually, a part being this a bold-face, you actually recognize the equation that you already had in 1D. And this is kind of, in my mind, reassuring. And then you go to computation. In that case, you have to kind of get into the details, and then you have to get indices of these tensors to pick up the particular component that are interest to you. And if you want to be even more efficient, instead of index notation, you can go to matrix notation, because luckily many of these tensors that you use are symmetric. So by saving a computational effort, you actually kind of profit from symmetry and put everything in matrices rather than tensors. So other than that, we are repeating the steps. In other words, we're going to recover again our strong, weak, and variational form on 3D elasticity this time to show you that looks very much like 1D elasticity. And then we'll go into development of these isoparametric finite elements. Basically, in 1D, we already introduced these elements. And we said this is the reason to have an appearance of each and every element of the same kind. For example, 2-node truss bar element to be exactly the same. And the process this element inside the same piece of code called subroutine typically. So basically, this is the same type of reason here. The only difference now in 2D and 3D, the case of isoparametric elements is also important to be able to ensure the convergence of the finite element method. In other words, to patch together the compatible type of interpolations of the, let's say, displacement field, a thing of this kind. And then there's much more, let's say, issues, what to put in terms of the numerical integration, how to handle these elements, distortion and things like that. So at the end, you realize there are many kind of rules which are not easy to verify. And there's one test which is called the patch test, which puts this to the, let's say, definite judgment. Patch test is simply the testing your element ability to represent a constant strain or constant stress field, depends if your material is homogeneous, of course. And basically, if you're able to do that, theoretically, you'll be able to converge. Converge, that means if you're really refining your finite element mesh, making your element smaller and smaller, the state of the element in terms of strain and stress will reach a constant value. So if your element is able to represent that, theoretically, you'll converge. Of course, the performance for the coarse mesh is definitely influenced by the quality of the element. And for that reason, we also study in this context on 2D and 3D cases, something called incompatible mode method, mixed formulation, which I will show you is the case of enhancing the performance of typical isoparametric elements and making them much more efficient opposed to a standard isoparametric element. I have to say that all the favorite elements in the commercial codes which are used by the people are rarely just isoperimetric. You always need some special enhancement to kind of improve the performance of these elements. However, really, one should always be careful when you're using somebody else's code to see what exactly these rules are. And basically, this element could be perfect for a certain number of cases and then not so good for other cases. I remember this was when I was working a lot on shells. There was something called obstacle course, where a certain program, which was very well known at that time for shells, was perfection to solve certain number of problems for shells. But if you start performing some kind of other solution, or you perturb the data on this problem, you realize these elements are not so good. So you can always optimize elements to be excellent in one way, but not necessarily in any possible way. So here in this method of incompatible modes, I'm trying to present something which has really a kind of good sense, a very broad basis of improving the performance of the element, no matter what you're trying to achieve. This has to do really with the completing of interpolation basis and things like that. We'll go along that when we go there. And then I'll probably skip, depends if I've done this membrane element with drilling rotation. What these elements are, this is some of the works I was doing after my thesis at Berkeley with Wilson and Bob Taylor, like postdoc. Basically, these are the membrane elements that have a rotational degrees of freedom. Normal continuum mechanics elements do not have rotational degrees of freedom, but we sometimes do need those type of membranes, because if you want to connect with the structural elements like beams, plates, shells, you would certainly need these rotations. So that requires revisiting theoretical formulation and so on and so forth. That is not in the book, but if you're interested in this kind of thing, I can give you a paper. It depends if I have time, I'll probably cover. If not, we'll just skip it. So let's delve into that and see what is in the shop about that. So direct ternary notation, indicial notation, matrix notation. So vast majority of the concept that we are using in mechanics, in 3D problems, that is the displacement field, strain field, stress field, are actually represented logically by vectors and tensors. In particular, displacement is a vector field, because if you take a coordinate system, x, y, z, it has a displacement along x, it has a displacement along y, it has a displacement along z. So you can characterize such a displacement as a displacement vector with the components of like the axis x, y, and z. Now, stress and strain is a derivative of the displacement, that is symmetric part of displacement gradient, and the stress is a product or linear combination of the strain multiplied by the elasticity tensor. We'll get back to that in a second. Basically, you have now in three-dimensional space representation of such a tensor as a 3x3 matrix. In particular, like a 3x3 that would be 9 components, but thanks to the symmetry of the strain tensor, and also thanks to the moment equilibrium equation symmetry of the stress tensor, basically you can get reduced down to 6. So representing this thing, you can do basically in terms of a direct notation. As I said, these are bold-faced letters that are now valid for any coordinate system. When you write a bold-faced letter, you're not talking about coordinate system, you're just talking an notion of a tensor. This will be like this bold X at the bottom line of this slide. And basically, when you go to computation, then you have to reach and get the component of a particular vector. So components are related to the choice of a coordinate system. And then the coordinate system, if you have 1D problem, will be such that you just keep one coordinate and that's it. But in 3D case, you typically need all three, X, Y, and Z. So engineering notation of, let's say, a position vector X, giving the position of each and every particle of a solid body, is given by this vector bold X. And in the typical engineering notation, you take a Cartesian coordinate system with Euclidean base vectors, I, J, and K. We put little arrows on top of that. And you have this projection of this vector X onto the axis X, Y, and Z. And you have the coordinates of this type of coordinates of this type of vector. Now, if you switch to indicial notation, this was done by using simply a product between Xi and Ei. So Ei are replacing I, G, and K, respectively. So E1 would be I, E2 would be J, E3 would be K, and Xi are just replacing X, Y, and Z. So the advantage of this notation, I don't have to write a long formulas. I can simply use a summation convention. When these indices are repeated, these are called dummy indices, you simply do the summation. So that would be like X1 E1 plus X2 E2 plus X3 E3, which is the same as this one above here, only with different notation. So this summation convention was introduced in Einstein when he was developing his work. Other than that, there's no relation to that. We are still sticking to 3D space. We are not thinking about 4D like Einstein was doing his relativity story. So basically, vast majority of developments, if not all, I'll be doing in the Cartesian coordinate system. So I don't have to go to a curvilinear coordinate system, which is typical choice of the early works on this theoretical foundation of continuum mechanics, books like Truzenol, Green, Zerna, and so on and so forth. These are really classical books, but as I said, not very easy to read because they have, from the start, have chosen the curvilinear coordinates. And then you have to distinguish between so-called covariant and contravariant tangent components, whether you do it with the primary or dual basis of this type of coordinate system. And then the coordinates are changing. For example, think of the polar coordinates. So if you take a derivative of the unit vector in the Cartesian coordinate system, and you have E1, 2, and 3, this is just I, J, K. These are vectors which are fixed in time. So whenever you take derivative with respect to time, it's 0. It drops out. But if you have something which is actually moving, you actually have to take derivatives. So this, in this curvilinear coordinate system, is typically handled by so-called Christoffel symbols. So every equation, if you look into typical development, for example, I created at the time the book of Nagli on shells. So every equation is like half of a page. And it's simply stating equilibrium equation or something like that, because it's so much clouded by this curvilinear coordinate system. That's the details that at the end you kind of start losing sight of what exactly we're talking about. So to make things simple, because it's possible in our case, we place development that we study in 3D Cartesian coordinate system, keep this unit vector fixed, the derivative in time are 0, and then taking out a particular component is simply done by the scalar product of this vector, for example, talking of position vector x with respect to a coordinate basis E1, EI, and then you simply do the scalar product of these two, you get the component xi. This is easy to show, basically, because you have orthogonality between this base vector E1, E2, and 3. They are unit vectors, they are orthogonal to each other. So basically, when you multiply EI by EI, you get 1, and you multiply EI by EJ, if J is not equal to I, you get 0. And so that really can be written here by using so-called Kronecker symbol. Kronecker symbol is like a unit matrix. It's equal to 1 when I and J are the same. It's equal to 0 when I and J are not the same. So basically, at the end, we take into account, as I said, symmetry of some of the things. And when it comes to real computation, we might place the components of these tensors and vectors into matrix, and simply, so that will be the notation for the matrix. Either you have a like real vector putting this into brackets, x1, 2, and 3, or you have a matrix, or you have a vector transposed, which is x1, 2, 3 written horizontally. So basically, tensors are just a linear transformation of a vector into another vector. So basically, if you take a vector u, you act upon this with the tensor, you produce another vector v. Now, this is a linear transformation, so I don't need parentheses. So it becomes simply a product between A and U. In terms of a matrix representation, it becomes simply matrix multiplication. So take matrix A with the components ij, that we're going, I and j are going from 1 to 3, and you multiply this with the component uj. So this will be spelled out here. So the component vi, if you multiply it with a scalar that ei, sorry, and then you have the tensor A multiplied by uj times ej. So introduce these guys inside, and then you call this component aij. This is a dot product between ai, ei, and the product between the tensor A and the unit vector ej. So you can write so-called, let's say, tensor product of ei and ej, and add on top of that the component aij. And this is the way you can write your tensor in some kind of direct tensor notation, which really is reminiscent, already give you the kind of appearance of a corresponding matrix with the component aij. Now, as much as you can do different operations with the vectors, you can also do the same operation with tensors. In particular, for example, we're interested in scalar product with two tensors. This will be needed when we are talking about weak form formulation, thing like that. So basically, you have something like a dot b. This is a scalar product with two tensors of the second order. So this is simply taking every component aij, multiplying by the corresponding component bij of the second tensor. So if you take a unit tensor, which we talked about previously, this is Kronecker delta, and you take like a scalar product with a particular tensor A, you get delta ij, aij, and now given interpretation of delta ij, that is 1 when I and j are the same and 0 if they are not, you simply recover the values of aii, that means a11 plus a22 plus a23, which is a trace of this tensor. These are the sum of the components of the main diagonal. If you talk about strain, this will something change of volume and things like that. We'll get back into that in a second. So basically, the idea is that once we have designed this notation, we are kind of able to reproduce the equation for 1D in direct manner. Only you will be having like bold-faced letters instead of thick letters. Now I try to follow the convention where the tensors are capital letters and the vectors are lowercase letters. However, if you go to epsilon and sigma, they are both stress and strain tensor. They'll be bold-faced, but they are actually second-order tensors, and they're actually lowercase, because big sigma would be like a summation sign, and big epsilon would be like E letter. And then basically, I tried writing a couple of papers like that, but 3 months later, I was not really I forgot what I meant by using certain letters. So some of the exceptions are allowed, I would say, because sigma epsilon is so much ingrained into mechanics that you don't want to touch it and change it. But most of the time, really, the convention that I said, tensors are uppercase, the vectors are lowercase letter, do apply. So other than second-order tensors, which produce vector from vector, we also have I-order tensor. For example, third-order tensor would be permutation tensor. It takes a vector W being a infinitesimal, let's say axial vector of infinitesimal rotation. And then this permutation tensor producing a skew-symmetric tensor W, which is a skew-symmetric tensor representation of infinitesimal rotation. So this, by definition, then third-order tensor, because you act upon the first-order tensor, the vector, which is a first-order tensor, and then you produce second-order tensor. Or, for example, I just said epsilon sigma second-order tensor. This is stress and strain tensors. And then you act upon the strain tensor by elasticity tensor C, which is now fourth-order tensor, to produce the constant equation. So you can see here that if you talk about elastic behavior in 3D elasticity, there are many more material parameters you have to define. Not only Young's modulus, theoretically, it will be like 3 by 3 by 3 by 3. That is 3 by 3 is 9, 9 by 9 is 81. So theoretically, you have 81 components, but it's not so bad. We'll go back to that in a second. So other than complexity in terms of the numbers and the details, what we're trying to cover here, at least in the formulation, I don't think you'll have any difficulty following that. Now, we also have to be efficient in defining the notation for the derivatives and the representation of these integrals and so on and so forth. So first of all, just summary, what we are representing in the particular case of a, let's say, thermomechanical problem, we have to have a scalar field, something like a temperature, then vector field, something like displacement, tensor field, something like stress or strain, and so on and so forth, possession vectors and so on. And then we'll have to do computation of the gradient, because all these fields vary for particular position vector x. So if I have a scalar field, I have like a gradient of a scalar field being given by a function f of x, it's just a scalar function of vector argument. The gradient of this is simply a vector. The component of this vector would be df, this function, the derivative with respect to xi times ei. These are the components with respect to any particular axis. The notation I often use is this nabla operator. Nabla operator takes a unit vector with associated partial derivatives. So for example, gradient f of x, I can simply write as nabla f. And that automatically reproduces this partial derivative and this ei into the same symbol. Now, gradient of vector field, like displacement field, would give you a tensor field, in particular second-order tensor field. So coordinates of this particular tensor field are given here. These are dvi, dxj, if you're talking about gradient of a particular vector field v of x. And then gradient of a second-order tensor will be third-order tensor, and so on and so forth. So basically, with this nabla type of notation, hopefully you can get comfortable with that, and then we can very easily represent derivatives as we go along. Now, divergence is the opposite way. If I'm computing the divergence of the let's say gradient of v, which would be like a second-order tensor, that becomes a trace of gradient of v, and that becomes a dot product between this nabla operator and v, that is simply dvi dxi. So this is some of the component of the main diagonal. Typically, that quantifies the amount of the mass that you're moving through a certain volume. Divergence is needed also on the stress field, because this gives you the change of the stress field with respect to external load to give you like a force equilibrium equation and so on and so forth. You can easily show that this happened to be the case. Divergence of A being second order tensor is VAIJ, it's related with respect to xj times EI, it's a vector. And you can show that this is valid for any constant vector U. You go through this development and you confirm that happens to be the case. So divergence is needed into strong form equation. In weak form equation, we need integrals. Now, we already met integrals in 1D case where you have only integration with respect to x-axis. So we have something called the fundamental theorem of calculus. When you have a derivative of a function, so-called primitive function g of x, integrated from a to b, it simply comes down to a value of this function at point b on one side, minus value of function at the opposite point a on the other side. So basically, this is the same thing here, only this is called the Gauss-Gradient theorem. Here you have a value on the boundary, which is corresponding to either a or b of the derivative of f with respect to xi. You turn this into a corresponding derivative or integral of the boundary gamma, just like it was here, just in the point. And then you have orientation ni, which is here given by plus or minus 1, and then the value of this function and this particular boundary. So this is done for the scalar field, and this is done for the vector field. That's actually how you recover. And then finally, for the tensor field, you have the same or similar type of development. So all these things are kind of put together in a nice way, and you can go quickly and master the 3D version of a elasticity problem as we go along. So let me now go into the steps of defining a 3D elasticity problem, and in the process, recover what is the main difference from 1D problem. First of all, the domain we are talking about is not possible anymore to represent as a single axis. You have to have at least 2D or 3D case. It could be any complexity of the domain. Here it's pictured in 2D case. I can have holes inside and so on and so forth. So whatever this part which is kind of shredded is a domain, and everything else is the boundary around. So the component I'm studying would be actually the domain omega. The thing around will be a boundary gamma, and this boundary gamma should be split into the gamma u, the part where I apply displacement, and gamma sigma, the part where I apply the forces. Even impose the forces to be equal to 0, I still impose forces. So how many of these points I have to have when I'm in 2D case? Basically, I have to remove the rigid body motion along x-axis. I have to remove rigid body motion along y-axis, and I have to remove rigid body rotation. So minimum 3 points of the supports have to be in gamma u. If you have a 3D case, when you have x, y, and z, you have 3 translation, 3 rotation, 3 translation along 3 axes, x, y, and z, and 3 rotation around 3 axes, x, y, and z. So you have to have a properly placed 6 support points in order to be able to define your let's say, a boundary condition and to turn this into a structure. Now, for this particular case, you need a definition. As I said, this is illustration. We have like a boundary is a gamma, whatever is inside is omega without bar, and then boundary and inside together are called omega bar. So here's an example. If I want to have like a circle and everything is inside, this is xy plus y squared equal or less than 1. Then omega without bar is x squared plus y squared less than 1, and gamma would be x squared plus y squared equal to 1. That'd be simple domain, which is simply a circle. Now, the solid body that we study, or structure or system, for us, it's a collection of particles. So each particle position is represented by this position vector. This is pictured in this figure here. You have a position vector for each particle. For us, this is all collection of this particle. So then I have to access the components of this position vector, xi, along the axis e1, 2, and 3. And then I also have to define a unit vector of exterior normal to be able to specify the corresponding boundary condition. So this is n, that's with some kind of a unit vector exterior normal. And basically, again, has to be assuming that the boundary is sufficiently smooth that I had to define. So again, I can place this in the matrix notation, which I'll eventually do. So in the three cases, you simply have x1, x2, or x and y, and you have these two components of unit vector x0 normal, n1, n2, the third component being equal to 0. So most of the development on IR2 street I'll do in 2D case, although the details for 3D case are typically not very laborious to add, but at least it's kind of faster and easier to go this way. So this one I already commented, as I said, the whole boundary should be connection, what you call it, the union of boundary wire imposed displacement and imposed stress. And you cannot have at each point both U and sigma imposed. Otherwise, you don't have a well-defined problem. You have something maybe like contact or something like that. And gamma U, as I said, has to be 3 for 2D problem, or at least 6 for 3D problem. Now, there are many books that are really talking about this elasticity problem from some different point of view. My favorite books happen to be Timoshenko, Sokolnikov, Gurtin. Basically, most of them are written by the people who have names which sound very much Russian. In fact, most of them are Russian. Guy who came to US in the time after World War II, let's say. And Timoshenko was professor in Stanford, as far as I remember. Then Sokolnikov was in Caltech, and Gurtin is still, I think, in Columbia. In Columbia, but with Carnegie Mellon and stuff. So basically, what's in these books, typically this is kind of heavily representing that catalog of problems that you could solve at the time of linear elasticity. And you have many, many kind of analytical solutions, semi-analytical solution, any method they could possibly use to solve the problem, represent what was possible at that time. In France, the kind of well-known book is written by Germain, Mécanique des milieux continus. He was professor at École Polytechnique and secrétaire perpétuel de l'Académie des Sciences in France. So it was a certainly influential book. And then Duo was a professor. He was my habilitation guy in Pierre Mercury. So also I had to write a book with a kind of typical French approach with the 3D version and all these things that I typically use. So then the notation we're going to be using is as follows. The position vector will be x, the component xi with respect to base vector ei. Displacement vector will be u with the component ui with respect to the base vector ei. Cauchy stress is the true stress. We are talking about small displacement gradient theory, where the initial configuration could be the one that is used to represent the true deformed configuration. So basically that the stresses are then the only true stress that appear on the deformed body. And it is a tensor of the second order, which has component sigma ij. It appears at first that it has like 3 by 3. That will be 9 component, but as I said, due to the symmetry that follows from the moment equilibrium equation, the sigma ij is the same sigma ji. You reduce down to a 6 component of this kind. In this notation, we use it ij, k, and l go from 1 to a number of dimensions, either to 2 or to 3, depends upon what kind of problem we are studying, 2D or 3D. So again, we are facing a problem mechanics, only now it's in 2D and 3D. So we have 3 fields. Now each and every of those fields is a little bit bigger. It used to be only a single component of displacement, single component of strain, single component of stress. Here we have 3 components of displacement. We have 3 by 3, 9 components of strain, and 3 by 3, 9 components of stresses. So we will need, if you want, 21 equations. So basically, first we'll have a kinematics equation to get the strain from the given displacement field. That is defining a strain as a symmetric part of the displacement gradient. Then we'll have equilibrium equation, which has 3 moment equilibrium equation, and then we'll have a 3 angular momentum equilibrium equation. And then we'll have a constitutive equation, which collect all the components of stress with the components of strain to follow the count with as many equations as number of components. So you can either go with ignoring the symmetry or U and epsilon and sigma, which we do nowadays in some interpolation, which are very useful for dynamics, because just one remark, finite element method is the best discretization method when it comes to statics. It has so-called the best approximation property in the energy norm when it comes to a elliptic problem, which is like elasticity or heat transfer stationary case. But when it comes to non-stationary problem like dynamics or non-stationary heat transfer, that's not necessarily the case. So you need something better. and you need some kind of interpolation which enforce continuity of stress or heat flux and things like that. And for that one, you have to abandon the symmetry of the stress. Now we start with statics, so we'll start with the symmetry of the stress, so we can reduce this number. You have 3 components of space and 6 components of strain, 6 components of stress. So you need altogether 15 different equations. And it will come from kinematics, equilibrium, and constitutive equation as we go along. So first, the kinematics. So the basic, let's say if we are talking about small displacement gradient theory, that means if you compute the displacement gradient, it will be second order tensor. This is this nabla U, which is a derivative of ui with respect to xi. Sometimes I take the comma here that represents the same thing as derivative. So sorry about mixing notation, but this is kind of historical, goes from one page to another. And I hope you get comfortable with all these different versions, because then it's easier to write. So basically, it is written in the tensor notations EI tensor EJ, multiplied by the corresponding partial derivative of component UI with respect to xj. And you can put this in the matrix. So in the matrix, you have like in the first column, the partial derivative of the first component with respect to x1, 2, and 3. Then partial derivative of the second component with respect to x1, 2, and 3. And finally, partial derivatives of the component u3 along the axis e3 with respect to x1, 2, and 3. Now, infinitesimal deformation is taken only as a symmetric part of this displacement gradient. First of all, I said hypothesis on a small displacement gradient theory would imply that each and every of these components is much, much smaller than one. We already illustrated last time the yield strain of a typical steel at 400 megapascal with 200,000 Young's modulus. The yield strain would be 0.002. So let's say each and every of these components is much smaller than 0.002. We are talking about this type of performance. So infinitesimal deformation means really this is very small because it produced from something which is like very small as well. This one plus this transpose, it is symmetric, obviously, with the way we are transforming it. And every component epsilon ij is now produced as a partial derivative dui with respect to xj plus duj with respect to xi divided by 2. Now, complementing this part would be so-called skew symmetric, where you actually subtract the transpose of the displacement gradient from the displacement gradient itself. So sum of these two, epsilon plus omega, gives me back my nabla u. And then this happened to be infinitesimal rotation. This is nothing to do with a particular, let's say, deformation. Typically, in the normal computation, simply ignored. We cannot get rid of that. We don't need it. The idea is that all these values that I said, talking about small displacement gradient theory, are very, very much smaller than 1. So if I now imagine the form configuration where the infinitesimal vector dx with the components dxj, when it's multiplied by something called deformation gradient, which is identity plus displacement gradient, we'll see when we go to large deformation why this deformation gradient plays an important role. I'm just reproducing this result coming back to the small deformation or small displacement gradient setting. You will actually have this to be identity plus displacement gradient, and given the displacement gradient is sum of the symmetric and skew symmetric part, I'm basically saying this is a sum of the skew symmetric and symmetric part. So what happened in any possible deformation, if you have 3D elasticity under the hypothesis of the small displacement gradient, is first you have an infinitesimal translation, you move it very little. Then you have infinitesimal rigid body rotation, which is given by this omega. That implies that basically with translation, you came to this dashed line. And then rotation will take it into the, like this is right angle, 90 degrees. You take it to new position. This is very small angle, where the sine of this angle could be replaced by the angle. And this is called rigid body rotation. You can notice if you really talk about length or something as a measure of deformation, length of this side of the triangle is not the same as the length of this part. Obviously, this one is larger. But with the approximation of the small displacement gradient theory, you consider this is 0. There's no difference between these two. In other words, this is just rigid body rotation. That's the approximation there. And then finally, in this direction, poof, you have some extension beyond this value, and this is called deformation. So how can you check that rigid body rotation does not really change any deformation? Well, you can imagine the case where epsilon is equal to 0, in which case the deformation gradient is identity plus omega. So you multiply identity plus omega times dx, and then I get identity plus omega times dx. That amounts to saying omega plus omega transpose plus omega transpose omega. Now omega is very small, is let's say 10 to the minus 3. So omega transpose omega is 10 to the minus 6, so we neglect that. And then transpose being the skew symmetric tensor is actually minus omega. So these two cancel. So by the hypothesis of let's say, small displacement gradient theory, you show that there's no change of the length of dx with respect to x prime. This is a kind of quick way how you can show that the infinitesimal deformation 3D case, it should be symmetric part of displacement gradient and not skew symmetric part. That one has nothing to do. Now, just go back to different interpretation. This is one way of interpreting this deformation simply in terms of the tensor and particular component. If you look into the typical engineering books at the level of strength of material, one has the tendency of distinguishing between something called axial strains, like dilatation. Then you actually have like a change of the let's say length along any particular axis. So this corresponds to a 1D version of y epsilon, like du dx would be du1, dx1, du2, dx2, du3, dx3. There's very large extension, dilatation, or compression along axis x1, 2, and 3, respectively. And the off-diagonal terms for this case will be basically something that is proportional to the change of the initially right angle. So these are shear deformation. Then you can take many other different strain measures. You can take something like a change of volume as opposed to whatever the complementary part and so on and so forth. And we'll go into that when we talk about constrictive behavior. But in any case, at this stage, I'm just happy to keep the strains without thinking what they are physically in this tensor, and to have their components accessible by taking the scalar product and getting any component I want, putting them into the table and so on and so forth to get matrix notation and so on. So this will be kinematics generalizing to a 3D case. I recover one part that I know from 1D, and I recover novelty, which is like shear deformation, which does not exist, change of the initially right angle, which does not exist in 1D. So if I go now to equilibrium equation, I can get, first of all, something that looks like a 1D case. If I ignore these indices, that would be sigma dx plus b. This is strictly speaking the equation of equilibrium for 1D case. However, here, these are actually 3 equations because you have indices I and j going from 1 to 3. So this sum up with the sigma 1, 1 derivative of x1 plus sigma 1, 2 derivative of x2, sigma 1, 3 derivative of x3 plus b1. And then you're there for the second one and so on and so forth. So basically, this gives you like a force equilibrium equation along the axis x1, x2, and x3. And then you have this moment equilibrium equation, which is giving you simply the symmetry of the tensor stress. Basically, sigma j is equal to sigma jr. Now, if you have a stress tensor, this was really the contribution of Cauchy to the theory of continuum mechanics. This was the first notion of a tensor. You took unit vector exterior normal. Typically, you can order your stresses into some kind of a, let's say, a table. And imagine these are the components that are sitting on the facets of a infinitesimal cube, which is aligned with the axis x1, 2, and 3. So you have these 3 by 3, you have these 9 components sitting around. And if somebody asks you, can you get me the stresses in any plane which is inclined with respect to this coordinate system? So orientation of the plane is given by the unit vector exterior normal n. You can say, no problem, I take a stress tensor sigma, I multiply with this unit vector exterior normal n, and I get so-called stress vector Tn. So this stress vector Tn is written as sigma ij times nj, with the components that are then written as I. That means sigma 1, 1 times n1 plus sigma 1, 2 times n2 plus sigma 1, 3 plus n times n3, and so on and so forth for the other components. Basically, you have something which gives you the possibility of writing the stress vector on any particular plane that you might need. So basically, the idea is that this Cauchy principle was the way of extracting the stress vector components for any plane that we need. And this is the first result with the notion of tensor appears. Unfortunately, it's a lowercase letter, but what can you do? It's still the second order tensor and stuff like that. So how did I get this equation? Well, basically, This is illustration of Cauchy principle, by the way. So I have my components here, sigma 1, 1, whatever, sigma 1, 2, 2, and so on. So forth, I have shear, and then I want to have the stress vector components. I need orientation of this plane where I need these components, and I'm like plus sigma, then I get this component Tn. So the equation of equilibrium is obtained simply by taking the whole domain omega, cutting out subdomain. So in this subdomain, I keep, it should have been B, not F, sorry about that. I have like integral over B, this would be like the bulk, the volume forces, integrating over the subdomain omega. And here I have a sigma times n, because this is the way you produce the stress vector, which is acting on the boundary to cut off. Now I use the divergence theorem. Recall here, we had a divergence theorem just a moment ago. I have a divergence theorem that I actually put stress tensor sigma times n. I can put it divergence of sigma over omega. Now this particular omega is omega tilde. This is subdomain that I have just cut out. And basically I have this divergence sigma appearing here. So then I can take omega tilde, which is like subdomain that I chose from a particular domain omega to be any arbitrary value, including shrinking down to a point. And for that reason, I get my linear momentum equation, giving me equilibrium, generalizing to 3D case, the sigma dx plus b from 1D case. So now you have all these components hanging in and so on and so forth. If I want to get moment equilibrium equation, I take the same type of subdomain omega tilde, cut out from the domain omega, and I take a momentum of this domain. Now this is correctly written as x cross product b, and this is x cross product sigma n. And then I work on that again. This amounts to x cross product divergence sigma plus b plus 2 times q times sigma. And basically this is already zero by the linear momentum equation. So I'm stuck with the skew symmetric sigma equal to 0 when I take omega tilde to be arbitrary. And that confirms this type of moment equilibrium equation, which makes the stress tensor symmetric and basically makes it into something that one can use sort of directly. So these are two equations of the kinematics expressing the infinitesimal strain field and of the linear angular momentum for the stresses are valid no matter what is the behavior. It could be a linear elastic, it could be non-linear elastic, it could be inelastic, it could be whatever you want. As long as you have small displacement gradient theory, these two equations are fine. Now, if you want to go into constitutive behavior, that's where the elasticity, inelasticity, and things like that we're going to be talking about tomorrow and maybe the end of the day will appear. We start with the simplest possible case to be linear elasticity, also called Hooke's law. So Hooke's law is a generalization of sigma equal to E times epsilon for 1D case. In 1D case, you just need a Young's modulus E. In this case, instead of Young's modulus E, you have to connect second order tensor sigma, which has 3 by 3, that is non-component, with the second order tensor epsilon, which has 3 by 3, also non-component. So together you have like 3 by 3 by 3 by 3, that means 81 component. That's quite a lot. So basically, if I really want to take a very exotic composite material, it appears that I would need to use 81 coefficients to define behavior, which is supposed to be linear elastic of such a material. Luckily, you know, there's a way of reducing this effort. Namely, you can have something called major symmetry, you can have something called minor symmetry. Major symmetry simply means if you change the pair of indices ij with respect to k and l, these values of C of elasticity tensor should be the same. This follows if you accept that your material is so-called hyperelastic, that you have internal energy, some kind of a potential, and then that if you take a first derivative of this internal energy, you get a stress. And if you take a second derivative with respect to strain, of course, you get corresponding component of the elasticity tensor. Now, if you take mixed partial derivative with respect to ij, epsilon ij, and epsilon kl, and then you change the order, you first take epsilon kl and then epsilon ij, these two things should be the same because you're coming from the same potential. So that's the reason you have a major symmetry. As long as you have hyperelastic behavior with the potential, all is fine. And then, given that the stress is symmetric, we just proved that there's a skew symmetric part of sigma is equal to 0. And given that the strain is symmetric, we have chosen strain to be a symmetric part of the displacement gradient. That would imply now when you change the indices ij with respect to ji, as well as if you change this kl as opposed to lk, again, these things should be the same. So basically, this already is reducing the number of the components we have to define by using this type of constraints related to major symmetry and minor symmetries. Then we also have to allow that if you study linear elastic behavior, for the moment things cannot go wrong, you cannot have instability. So the tensor elasticity tensor has to be positive definite. What that means, if you have a strain which is any arbitrary strain, and you multiply this with the elasticity tensor, you get the stress, then you multiply again with the same type of strain, the value has to be either positive or zero. And it could be zero only if the strain happens to be zero. If any kind of other strain, you have to have a positive value, because this is actually stored energy that you put into material, and there has to be a positive value. So we're storing something positive, you cannot be pumping out of the in elasticity out of the material. So as I said here, it already is a major symmetry is the consequence of a potential. In other words, if you have a linear elasticity or stored energy, simply quadratic form, it could be written as 1/2 epsilon ij times c ij kl times epsilon kl. This is equivalent in 1D writing that the internal energy is like 1/2 epsilon times e times epsilon. Now, minor symmetries, I already commented on that, are the consequence of the symmetry of the strain tensor and the stress tensor. And all these constraints can help us reduce the number of coefficients to the smaller number as opposed to 81. Now, what's the minimum you can really imagine? Well, the last kind of possible reduction is reducing this to 2 coefficients. In other words, you have something called for linear elastic, homogeneous, and isotropic material. What that means, you have a response to be the same in each and every direction that you might have chosen. So basically, you have something called autotropic. Typically, wood is a autotropic material because you have like fibers of the wood of the let's say trunk of the tree goes into one direction. Then perpendicular to that, you don't have the same resistance because you don't have those fibers. And many composite material with the long fibers, they have the same type of principle. You have a resistance along the fiber and then resistance perpendicular case. So something called orthotropic material. If these things are not aligned with the 90 degrees, well, you can have anisotropic and so on and so forth. If isotropic, that means behavior is like the same, whatever is the preferred direction you want to study in terms of this behavior. So in this particular case, so happens that one can characterize the behavior of material only in terms of 2 coefficients. One is, there are different choices how you can choose these coefficients, but basically the idea is that the most convenient choice when you write in this index notation, if you want to represent the tensor in a very compact way by using so-called index notation, you can choose so-called Lamé coefficients, which are lambda and mu. So lambda is written nu times e divided by 1 plus nu, 1 minus 2 nu. So E is again Young's modulus, and nu is something called the Poisson's ratio. And mu is actually something like shear modulus. So this should be E divided by 2 plus 1 nu. Nu here is extra, so this is a typo. So kick it out, please. So basically, the idea is that you can quantify the behavior of the elastic material either by using these Lamé coefficients or this Young's modulus and Poisson's ratio. In fact, I like to remember this in a very nice way. Say if you have something like a typical, let's say, if you have something like a typical specimen that you are testing, and then here you apply some kind of force. Let's say here it would be something like a sigma 1,1 type of situation. So what happens, let's say if this is part which is constrained, you cannot move it there. So what you will have is like you will have a specimen which is being deformed, something like that. And if this is a deformation here, this will be something like a length of a specimen times epsilon 1,1. So let's forget about length. Let's say this is equal to 1. The length is equal to 1. So I can simply say that this is sigma 1,1 as the only component divided by E. So that recovers my 1D case. But you notice for all normal materials, there's also this part here, which is let's say epsilon 2, and so happens that, oops, 2, and so happens that this one is written as a minus nu times sigma 1 divided by E. So typically nu could go larger, smaller, equal to 0.5. That would be like a incompressible material. For normal materials, should be going larger than 0. But then you have some kind of crazy material that you can get from at the nanoscale and stuff like that. You can have something that nu could be even negative. But the idea is like typically for the positive values, and I'm focusing on that. When you pull the specimen in one direction, then it shrinks in the opposite direction. Typical values, I don't know, for steel will be 0.33, or for concrete 0.16, and so on and so forth. So this is the kind of that we want to take. Okay. So again, this would be then the type of thing that you use. Either you take the usual, let's say, engineering type of properties like Young's modulus and Poisson's ratio, or this Lamé coefficient that you can produce from this to write this in a more compact way. Now, in the cases when you study material which are sensitive to the change of volume, often the type of coefficient that one is using are so-called bulk modulus, and then shear modulus the same as this mu. Bulk modulus gives you the ratio between the change of volume and the hydrostatic pressure, and the shear modulus gives you the ratio between the change of shape and the shear stress. So you can have like at least 3 different ways of characterizing elastic materials. So Lamé coefficients, Young's modulus, Poisson's ratio, or bulk modulus and shear modulus, and so on and so forth. And then we're going to stick with this because really there's no point. We can go for 81 coefficients, studying any composite material you want. It will just more details. But in reality, the steps are the same, just like the case when you have a simple elastic, homogeneous, and acidotic material characterized with only 2 coefficients. So one more on top of Young's modulus, and you are in 3D business, no problem. So at the end, boundary condition have to be applied. Again, it has to be either imposed displacement or imposed stress. For each and every component, I have to define what is imposed displacement, what is imposed stress, and they have to not be applied at the same point. So, for example, if I want to take, where's my whiteboard? Stop share. If I want to go to the whiteboard again, up. If I take a specimen like that, so here I have to have 1 support, 2nd support, and the 3rd support. These are the only things that belong to gamma U. And all the other things are something like a force. So here typically you apply a force, and that is something called the 3-point bending test that is used often in a type of quasi-brittle material that for testing the tensile strength and things like that. Now, if you have a 3D version of that, because the specimen is really not 2D but 3D, basically you have it something like a box. And then you can kind of generalize this, so you recover these 3. Then you can put the 3rd one that takes taken there. Then you have to kind of remove something that you cannot rotate around one axis. And the only one that I'm missing, I don't know, somewhere that is this. So it should be something like around this axis. And anyway, so basically that would, or basically to be able to kind of to be able to guarantee the stability of a particular structure. So this is actually what is my definition. Now I take these 3 equations, I mix them together, just like you did in 1D case. First of all, I take the kinematics, how computing epsilon, and put it directly into the way of constitutive equation, how to get the stress. Then I compute divergence of stress, which is now written as a C times symmetric part of the displacement gradient plus B, and I get my equilibrium equation in 3D elasticity case. Now you notice here that U comma L are this partial derivative of duk with respect to dxl, and then again derivative with respect to xj. So these are second order partial differential equation. So no wonder that many of these illustrious books had to be written about how to solve these second order partial differential equation for very special cases. Again, these are a couple hundred pages or even more books, and there's not a tremendous amount of examples that you can solve with such an approach. But still, there are a certain number that are always useful for testing your performance of the numerical solution and so on and so forth. So then you can also impose your displacement, and you impose your stresses, which are expressed in terms of displacement. And this is the way you're kind of defining it, your strong form of boundary problem for linear elasticity. So main difference from 1D case is that unknowns are now vectors and tensors, but on the other side, that looks pretty much, and then we have partial derivative because we have more axes, not only one, as opposed to ordinary derivative in 1D case, but more or less it's kind of the same thing, and just we have to compute all of this and the same way. Now, the same critic that we already said in 1D case, it was fairly easy to integrate 2 times. In partial differential equation, the kind of complex domains, it's much less easy, and the number of cases that are possible to solve is certainly limited. So basically, what people were doing went to a weak form solution and trying to find these approximations. So again, we follow the same path. We say, okay, we're going to give up on verifying all these equations in each and every point of the domain X. We are going to do the averaging. So this averaging will be chosen in terms of the weighting function. So Wi would be a component of the weighting function, which is following the radial displacement field here. The only difference would be that you have the same irregularity, that is the functions is square integrable, and the first derivative is also square integrable. That means you have a finite energy space when you're kind of approximating this type of thing. And the difference is that real displacement field has to have this imposed displacement value at the boundary where you impose it, whereas the weighting function has to be equal to 0 at the same boundary. Because there we know the value of the displacement, there's no way that we have to kind of go and test something because already it's known. So then we take this integration by parts and multiply this strong form with a weighting function, then integrate by parts, reduce the order of derivative that appears on the, let's say, stress, which is sitting here. We get rid of this derivative, comma j, push it over to the weighting function. So you get the symmetric part of weighting function because it's a conjugate to symmetric stress. So symmetric part drops out. And then you end up having a weak form, which compares the, let's say, work of the internal forces and work of the external forces. What we already said, this is also called the principle of virtual work, where it says that when the work of the internal forces on some kind of virtual displacement W, which are the same as weighting function I just described, matches the work that is done by the external forces of the same virtual displacement, then obviously you have equilibrium. Now, one has to refine this statement here, because when you have this integrating over the boundary gamma sigma, you have to go back and you actually to unravel for direction 1, direction 2, direction 3, and so on and so forth. It might not be the same one. So basically, you're splitting it in a way that is convenient for the each and every type of boundary. Okay. So one can actually show that these two things are equivalent. For that one, you need the auxiliary result that shows that when you have a scalar product between symmetric and skew-symmetric tensor, you see here I kept only symmetric part because this part here is symmetric. So how could I do that? First, I take a Euclidean decomposition of second order tensor. Sigma ij is equal to symmetric sigma and skew-symmetric sigma. Skew-symmetric is supposed to disappear. And then basically symmetric is get by sigma plus sigma transpose divided by 2, where skew-symmetric is sigma minus sigma transpose divided by 2. Here I kept this uppercase letter for generic type of tensors. And then you multiply this by symmetric tensor. So basically, it reduces only to a scalar product between the symmetric part of this A and S. Skew-symmetric part is automatically eliminated because of this property that the transpose of this is equal to minus, so they cancel conveniently each other, and you're stuck only with the symmetric part. This is shown here in the kind of detail. So that allows you to make a proof for the weak form, or you take a, let's say, multiply this weighting function with this force equilibrium equation, and then W here is missing, or a parenthesis kind of wrong place. Anyway, it doesn't matter. Then I integrate this by parts. I shift this derivative of sigma to W, so I recover the symmetric part, and the process I recover this part here. Here I take a divergence theorem. I get my boundary condition, that is one part, or gamma, which is W0, so I cancel this, and the other one with the gamma sigma. This is called T bar, and at the end I recover precisely what I call the weak form. So the conclusion from this development is that when you start with a strong form, you can always go and obtain the weak form without any difficulty. Just follow the steps and you get there. On the other side, if you start with weak form, that is your starting point, to get the strong form, you can do that if you kind of get more than what you argued for, because when you start, you don't really need regularity of stress field in order to be able to compute derivatives. And when you end up here, you need this regularity in order for this result to be valid. So assuming you can do that, it's not always the case, but let's assume you can do that from the finite element solution. Any kind of finite element solution, you might not be able to do that, but imagine you could. You can obtain from this development when you kind of inverse the order of the integration by parts. Basically, the goal now is to get rid of the derivative of W, to put it back into here, and you get it on sigma. And so basically, again, following the steps and the boundary, let's say, conditions, you obtain this so-called Euler-Lagrange equation of this type of functional. This will give you the linear momentum equation, equilibrium equation, and this will give you the expression of your boundary condition for the imposed stress. So in this approach with weak form, you have something called the essential boundary condition. This is imposed displacement. In other words, when I go back to the weak form, the only boundary condition I impose is the one on displacement. I do not impose the boundary condition on the stresses. They are recovered naturally from my weak form. So that's often, these are called essential because they're essential, they are there. You have to have this in order to guarantee the kinematic admissibility of the weighting function, whereas the natural boundary condition are not necessarily needed because they are recovered directly when you are going through this development. You get back in your weak form that you get imposition of the natural boundary condition as you go along. Okay, so once I have defined all these equations, the strong form, weak form, now I can, in my tensor notation, I can now start worrying about efficiency. So the idea here would be to kind of reduce the number of components that I have to operate upon by taking advantage of the symmetry of stress and strain field. So I'm now defining the matrix notation. I put this vector U into matrix notation, so we like in 2D, just two components, U1, U2, and the same thing for the W with two components, W1 and W2. Now the formation tensor, in 2D case, you have epsilon 1, epsilon 2, 2, epsilon 1, 2, epsilon 2, 1. It's a 2 by 2 matrix. I can pack it into this vector with three components only, where I put this dilatation epsilon 1, epsilon 2, 2 into first component, and the last one 2 times epsilon 1, 2. It's just a choice that was really taken by many people who started developing the codes, and then people kept taking it. Some people use after the tensor notation and so on and so forth, but again, it's just a choice, very arbitrary choice. So basically, recall here, epsilon 1 is computed as a partial derivative of U1 with respect to x1, epsilon 2, 2 is partial derivative of U2 with respect to x2, and 2 times epsilon 1, 2 is actually what we call engineering shear deformation. It's total change over initially right angle. And it's computed as partial derivative of U1 with respect to x2 plus U2 with respect to U1. If you want to get illustration, this way something like that. You know, initially you have let's say, initially you have something like infinitesimal element, and this is x1. and this is x2. So if you want to have like a change of this angle here would be a change of u2 with respect to x1. And this angle here would be change over u1 with respect to x2. And then you have something like that as a deformed shape. So basically, you can see that with the shear deformation, this is the total change of the angle. With the shear deformation, you actually do not change the volume, but you just change the shape of this particular stuff, and you can put it together, all together to handle the shear deformation. So I can do the same ordering for the virtual deformation tensor. In other words, I can compute the corresponding components of virtual displacement, virtual deformation tensor by taking virtual displacement W, and then doing the same thing, only replacing U by W. And this is all written here. So basically, after that, I want to see what do I do, how to peg the sigma. So the goal is to keep the energy-like product with the same meaning. So normally, if I take a tensor notation, energy-like product is 1/2 epsilon ij times sigma ij. That amounts to saying epsilon 1 sigma 1, epsilon 2 sigma 2, epsilon 2 sigma 2, epsilon 2 sigma 2, because they're symmetric. So that happens to be 2 times epsilon 2 times sigma 2. But in epsilon, we already had 2 times. So in sigma, we only keep 1. And at the end, this is how we do the packing. So here I now want to see how to pack the elasticity tensor. So basically, the idea is like you can have a like elasticity tensor in matrix notation. I start with elasticity tensor in tensor notation, Cij, which is mu and lambda, with this conical symbol. Then I write all these components, sigma 1, sigma 2, sigma 3, sigma 1, 2, sigma 2, 1. I only kick out the other one that are not related to sigma 1, 3, whatever. This is like kicking out epsilon 3 and epsilon 2, 3 and corresponding stresses. And then I simply take the components Ij and Kl and look into this equation to obtain what I get. For example, if Ij, K, and L are equal to 1, this delta 1, delta 1, this delta 1, this 1 and 1 is 2, so I get 2 mu. And here delta 1, delta 1, I get 1 lambda. Then if I get I and j, let's say 1 and 2, and KL, I and j are 1 and 1, and K and L are 2 and 2. So basically, when I is equal to 1 and K is equal to 0, this cancels. When I equal to 1, L equal to 2 is cancels. And I get only here I and j are 1, K and L are 2, so I get lambda. So I get only lambda, and so on and so forth. So simply by reading this and writing it into the table, I can get my let's say, constitutive model that is related here. But now I want to reduce it to Dewey case. And it's not enough only to kick out epsilon 1, 3, epsilon 2, 3. You have to worry about the others. So basically, you can have something like here is like also take into account the symmetry. Take into account epsilon 2 is the same as epsilon 2, 1. And this is gamma 1, 2 over 2. And I got now this one. And now you have two different cases. One case is so-called plane strain case. This is something where I have a very long structure, something like a tunnel, and you want to study only one, let's say, slice of this structure. And you see the structure is so long along this axis that you place the axis in the direction of x3, that there's no deformation in this direction. So you can kill out epsilon 3, 3 in this type of line, and reduce it to epsilon 1, epsilon 2, 2, epsilon 1, 2. But if you do that, you can reduce your D to be lambda plus 2 mu, lambda, lambda, lambda plus 2 mu, 0, 0, 0 mu. Well, lambda is this and mu is that, but again, mu is not, should be here. You should be able to recover sigma 3, 3. Hopefully it's here. The sigma 3, 3 not necessarily equal to 0, only epsilon 3, 3. And you recover this in post-processing. Another way of writing this is in terms of inverse, that you can write epsilon 1, 1, epsilon 2, 2, 2 times epsilon 2 to be 1 over E, 1 minus nu, and so on and so forth. It's just the picture I was plotting a moment ago, where you have when you extend it one direction, you have a shrinkage in that direction for positive value of nu. So this is the plane strain case, or even epsilon 33 is equal to 0. You can also have a plane stress case when you have a very thin structure, something like a wall or sheet of paper, and you load it only in its own plane. You can say the stresses on the surface which are not loaded are equal to 0, and given that the structure is very thin, you can extend the hypothesis sigma 33 is equal to 0 throughout the domain. So doing that, you can actually express this for the extra equation, which is sitting for sigma 33. You can get that epsilon 33 is equal to 1 over lambda plus 2 mu times lambda epsilon 1 plus epsilon 2. This is the kind of thing that you have here. And then you plug it back into the first two equations, and you can write it again as lambda plus 2 mu, lambda 0, lambda 0, 0 mu. But this guy is not just lambda like here. It is also lambda bar, and this lambda bar happens to be 2 lambda mu divided by lambda plus 2 mu. Or if you have a typical of these plates and shells, if you write it in terms of Young's modulus and Poisson's ratio, this will be like E divided by 1 minus nu squared, and then 1 nu 0, nu 1, 0, 0, 0, 1 minus nu divided by 2, and so on and so forth. So this is the way I'm packing all my weak form, which was written here in tensor notation. I have doing nothing else but repackaging this into matrix notation, and I write it now here. In other words, these are now notation I introduced. Please don't get confused. The E is now like an operator where I place these strain components for real and virtual strain. So this is a vector, 3 by 1 vector. No longer the base vector because there's no index. Or there's only that many letters. What can you do? So basically, the weak form is written like this Galeckian equation, which is a UH semicolon WH, that because it's always linear. Here would be a transpose vector of virtual strain times the stresses, which is D times the real strain, minus the work of the internal forces, WH transpose B, and WH times T. So now we have to unravel what it is. And basically, we have to construct the approximation by using the finite elements. Now, things get a little bit more complicated, but not that much, in the sense that the domain is 2D and 3D, and it's not so easy to cut it into like simple pieces like in 1D case. In 1D case, representation of domain is always exact because you have no other choice but simply to take how long is the interval that belongs to a particular element. However, 2D, 3D case depends on what kind of element you're using. Often in real life problems, you have a curvilinear boundary. If you have a sports car, it's always some kind of nice shape that people like to buy. And then you have to represent and do the computation. So really, high-order elements that are able to represent this in a very nice form turned out to be very sensitive to distortion. We'll talk about that in a moment as we go along. But so people prefer by far low-order elements, either like a triangle elements, is there any triangle here? My God, I don't see it. Here, like this triangle here, or like quadrilateral elements or things like that. So these elements have straight edges. They are some kind of quadrilateral or triangular, and there's no way they can cover the real boundary here. So you always have an approximation of the domain. In other words, you can say that omega h is already approximation, which is constructed by the representation of your true domain omega by assembly of the finite element nodes or subdomains. And that's not necessarily the same. How can you improve this approximation? Well, you put more and more elements, or you put sort of higher order elements and stuff like that. But anyway, this is the kind of error which always stays in your problem. Nowadays, I've seen that development a lot. It was done by isogeometric elements, and people take nerves to represent this domain very nicely. But again, the nerves are no longer using polynomials, and the general solution where you can have a so-called, let's say, best approximation property with polynomials or partition of unity type of guarantee and things like that are no longer guaranteed. So you can have a very good solution for a special problem, but you can also have surprises for some other problems. And one has to kind of worry about that as well. Anyway, the idea is like we'll stick to our polynomials and explain that because it's a vast majority of computer codes are using that. So basically we'll have to learn how to construct now the interpolation over the typical triangle elements, quadrilateral elements, and so on and so forth as we go along. So we split that in the element point of view, and then build it together with the element type of computation, what we call finite element technology. At the end, we'll do the assembly and recover the whole type of thing. And really, the big power of finite element method is the fact that we're able to take a complex problem, split it into the a bunch of the simple problem, particular elements, but again, worrying about continuity of the displacement field as we go along from one element to another. And basically, this is the idea that is now going to be discussed. So here's some notion that we have to introduce. First of all, by defining our finite element mesh, we have also defined our nodes. In other words, if you look into this picture, every corner here is a particular finite element node. This is where we're going to place the unknown values of the real displacement field and also virtual displacement field. And everything else inside will be covered by the particular shape function that we want to choose. Now, some of those nodes are sitting on the boundary, which is called gamma u or gamma g here. That is what I have imposed displacement. So for this boundary, basically, I'm no longer obliged to do computation because I already know the value. So these boundary nodes are taken out from the total set. And this way, I only define the number of equations, the number of nodes for unknown displacement. For any particular node, I can also have like one component is restrained, one is not. So even if it's partially free, you can still have to take it into number of equations. Now, let's say number of equation times the number of degrees of freedom. Again, this is the idea, like if every node has the same boundary condition, then you simply multiply by 2 or 3 if it's 2 or 3-dimensional problem. But again, it could be for some cases that the node has a one constraint in one direction, but not the other. So it has to be a little bit more subtle when you go around. Typically, you go the sweep of the finite element mesh, you see what are the constraints. You kind of put it on the side, you put this equation at the end, and all the active equation, that means the unknown displacement, you put up front, and this is the one you're computing. Once you computed the active part, then you go into the, let's say, this reaction part, and this is the way it works. Well, basically, this could be something that I should have actually asked you to do in some little homework, but we'll get back to that in a second. Maybe before I actually do that, why don't you try to do that, because this will give you a little better understanding what I'm trying to say. Imagine if you have a like a bar, and this is here the constraint, and here is a u is equal to u bar. That is the given value. And here you have like a 2 elements. So this is like unknown values are u1, u2, u3. So I put the t here, t bar, and I put my b distributed load in this direction. And I want to solve this. So first solve this by, let's see if I can use the text. What the hell is the text? Text is here. So here's solve this with the 2 elements, 2 node truss. Then 2, solve this with 1 element, 3 node truss. So the idea, like you have to have this solution, and then here compute u of x, epsilon of x, sigma of x, and compute reactions. And check if they match. Okay. Is that okay? So you can take this a little bit to see the steps, because the last time I don't think I gave you this homework. It'll be kind of good enough. So hopefully you can take your phone and take a picture. It should be small enough to remember without any problem. Okay. So basically I can go back and carry on with my development here. So now when I have decided what the mesh is and what the active nodes, I start by constructing the finite element interpolation for the virtual displacement, which in the component, this could be like shape function NA of x, multiplied by the corresponding component of this virtual displacement at node A in direction I. I can put that in the vector notation to take all the vector field W of H is equal to the scalar function NA. They are the same for each and every direction, times the nodal values of the virtual displacement. I take the same thing for the real displacement field. The only thing, eventually, I add the correction for the displacement which I imposed. So if there's no displacement which is imposed, they are all zero. This will be the same like a virtual displacement, but I have to have extra term which is giving, take into account the kind of contribution of this imposed displacement at the boundary, which will be the case for the small homework that I just gave you. So basically, once I have constructed these shape functions, please note that these shape functions should be as usual. They should be like equal to 1. If this is node A, they should be equal to 1 at node A, and they should be equal to 0 at all other nodes. This will like definition how I can then take these shape functions. So with such a choice of shape function, the nodal values of these displacements are really, the WA are really nodal value of virtual displacement field. And so the A is really nodal value of the real displacement field. So once I have constructed these shape functions, I can then obtain the computational derivatives and basically get the strain field interpolation. This will simply go through the processing of this vector E. Recall E was placing the strain components in this vector. So the first component, epsilon 1, 1 is simply derivative of U1 with respect to x1. Epsilon 2, 2 is derivative of U2 with respect to x2. Epsilon 2, 1 was a derivative of U1 with respect to x2 plus derivative of U2 with respect to x1. So if I go back to this type of computation, this way I can define matrix B that is giving me the product between the strain components and the nodal displacement vector. And for duty case, this will be like d1, dx1. I just have a d and a dx1 because d1 will be in this vector here. So goes also here, d and a dx2, because d2 will be in that vector. And here will be d2, dx1, d1, dx2. Basically, I have it here in the shear part. If I have a 3D version, it will be extended. I'll have like the third dilatation and 2 other shear deformation to have this matrix B. So then I have what you call it, a final writing of my weak form in terms of the Galerkin equation, where the virtual, let's say, deformation measure times the stresses, which is the constituted matrix times the real strains, minus the work of the external forces, has to be equal to 0. Now I say this Galerkin equation implies summation of all 3 virtual displacement at the nodes A in direction I, multiplied by the residual. And the residual can be written as a so-called stiffness matrix, multiplied by the nodal values of real displacement, minus the work of the external forces. And now I can say that for any arbitrary value of this virtual displacement that is not equal to 0, I can then enforce that the component of this residual has to be equal to 0. So this latest residual method again comes back to the rescue, and the final product of my development is a set of algebraic linear algebraic equation. Now the only difference from 3D case, I don't have here directly A, B, and B as I did in 1D case. I now have indices which are P and Q, simply because for each and every of these nodes, I have more than 1 degree of freedom. So basically, I have to have like a connectivity matrix, which takes into account particular node and particular direction. So by combining this node and direction, you can have other index to be P, and combining the other node and direction could be index Q. Did I write it somewhere? Hopefully. And then, yes, for example, P is equal to number of degrees of freedom, A minus 1 plus I. Q is equal to number of degrees of freedom, B minus 1 plus J. So basically, this way you can store all the degrees of freedom in the table, and you can write the forces of the like equivalent nodal force for the 3D case, and you can write the element stiffness for the 3D case. You know that if you want to extract each and every component, this is the way you do it. You have your elasticity matrix, which is coming from elasticity tensor. You have this B matrix, which has been obtained by computing the partial derivative of the shape functions. And here you have your loading and the approximation of the let's say load that you have to define, and so on and so forth. So again, the final product is nothing but a set of algebraic linear equation Kd is equal to F. So what we learned in 1D case will not change. The only what will change is profile. In 1D case, if you have a numbering of these nodes 1, 2, and sequentially all the way to the end, this K matrix will be tridiagonal. Here, it depends on the numbering. You can have very wide band or a small band. It depends really how complex is your domain. The goal, again, to reduce the band as much as possible to have the smallest number of operations as we go along. So on the other hand, I just have a set of linear algebraic equation, so there's nothing to stop me to use, again, my Gauss method to do this triangular decomposition of matrices U and L, lower triagonal, and upper diagonal matrix, then do forward reduction and back substitution and obtain the value of D. So once I obtain this value of D, I have everything. Basically, I can go back and obtain my strain by using this interpolation for the strain that I have defined here, that in this case, basically, and then computing this, multiplying with D, I have my stress vector, which is written here. And that's the end of the story, typically. And then I ask you also to do reaction, which will be from this extra equation that you have in this case. So where the finite element method enters now, it's again this technology of the finite element is basically by writing this global system by taking into account the local contribution of these elements. So you have like an element stiffness matrix Ke and element nodal force Fe. And basically, you can get this by the assembly of the finite elements. So this assembly is pretty much the same as 1D case. Again, only difference is you have to enlarge the connectivity matrices to fit all these type of things. So basically, we will have to do that on the element basis. And this is what I wanted to discuss. So basically, the idea is that follows. I have my computational stiffness matrix and my computation of my external load vector for each of the element. So I have to be able to define a particular contribution of this particular element. So I start by computing, for example, if I take into account the stiffness matrix, I have to have like a B transpose B times B to be computed over the whole domain omega H. So I split this domain omega H into a number of these subdomains called finite elements omega E in such a way that the assembly of this omega E, when you put them all together, touching one next to another, you obtain something like omega H tilde, which is approximation of my true domain omega H. If I look closely in what I'm supposed to be computing, here you have derivative of dna dnx, dna dnb dx. A and B sometimes could be the same, sometimes could be different. But in any case, I have to be able to justify that computation of this kind will be possible. Hence, I recover the interpretation of my convergence criteria. In other words, I say that, again, I want my functions to be sufficiently smooth inside each and every of these elements so that the first derivative is always unique. This way, I don't have to split my integration domain omega E into some kind of subdomains in order to have this smoothness. Then I have to have a continuity over the whole domain. In other words, when I go from one element to another along the same boundary, the two elements should be sharing the same interpolation. And in 2D case, this is a bit that people do not understand. Initially, when I remember talking to people who are not used to finite element, they thought they were just like, stapled with this agrafe, with the same French. at the nodes, but don't really have to be also glued together along the boundary, at least for this case. If you go for high order shell theories, they have to be also first derivative and stuff like that. So it can be quite complicated. Why do they have to be glued at the boundary? Well, because when you're computing these things and you take a derivative, then given that you have like a and B are the same, you would have something like with a jump and given by Heaviside, you have like a delta Dirac. And then given that A and B happen to be same, you can run into the situation where you have a Dirac square, which is something which is not defined. As much as Dirac itself is defined, you get value of the function at the point where Dirac is. Dirac square is not defined. And then finally, the sum of these polynomials, NA over a particular element, they have to sum up to 1. That's what we said is the notion how to build a, let's say, approximation for the, let's say, rigid body motions. Because if one element is not loaded, it's sitting in the part there, all the space on this side of the should be equal to 1 or to be the same, whatever is the value. And then basically, if you pull it out, you get your interpolation to be the same like the nodal values. And that is guaranteed if the value of the sum of these shape functions amounts to 1. So this will go then into these elements. What I noticed, there's a triangular elements and there's a quadrilateral element. So we start with the simplest one with the triangular elements. So we're close to 10:15, where I promise we have a break. Let me just take it up. Okay. Do we have any questions or comments? Do we have a... Okay, no problem. Whatsoever. Good. So let us then take a break 10:15 until 10:30. And we come back there, okay?
Okay, thank you, Professor.
Shit, I was not recording.